Material Testing System machines, or MTS, that are shown on this slide from MTS website, are machines that are used to test specimens for their mechanical properties. Tests such as tensile, shear, compressive, bending, on and on could be done with this for specimens in this equipment. It has a fixed grip and a mobile grip, and the loads that could be applied to specimens are either displacement control, which basically determines how much you want to move or how far you want to move this mobile grip in the vertical axis, or the force control, which means how much force you want to apply to the specimen. In this example, we want to take a look at a specimen in this shape, which is one of the standard specimens shown in ASTM standards for material testing for basically metallic elements or materials, to practice some time history post-processing, some modeling techniques, and displacement control loading on a specimen that is shown in this picture. The material properties are given in this table, similar to an aluminum material, and the dimensions are given in this image. The total height of the specimen is about 16 centimeters. We have 9 to 11 plus 5, 16. We have radius of the fillets 1.5 centimeter, and the radius of this smaller section, or the neck of the specimen, is 2.5 millimeters, and the radius of the top part, the bigger radius, is 4 millimeters. We want to apply a 2 millimeter ramped displacement at the top surface at the duration of 30 seconds and define 10 sub-steps in that 30 seconds and save the results, or all the results, for all the sub-steps. The bottom surface of the sample will be fixed, and then we want to plot the element solutions for stress and elastic strain in the y direction at the final load step, which is the 30th second. And then we want to define a vertical path at the center line of the sample and map the y direction stress and elastic strain and see its changes. And we also want to plot or print those path items. Next thing is to perform time history post-processing, and we want to obtain the elastic strain and stress in y direction for a single node, and then print and plot those materials, and then use those values to find the Young's modulus and Poisson ratio of the sample, which for this case, because it's a linear elastic, we're expecting to have the same values that we give in the material properties. But in case we had laminated composite material, then this would give us the Young's modulus and Poisson ratio in different directions for the composite material. Now, with that being said, let's go to ANSYS and solve this problem. So here I'm in ANSYS, and the first thing I want to do is to define some parameters. For the big radius, which is the radius of the top surface or the top portion, I'm going to call it 4 millimeters. And then the radius of the smaller section, or the smaller radius, was 2.5 millimeters. And then the radius of the fillets was 1.5, I didn't type that, 1.5 centimeter. The total height of the sample is 16, but I want to define the top half first, so I'll call it 8. So total height is 8 centimeters. The tap height, which is the height of the section with the big radius, was 2.5 centimeters. And the height of the ramped section was 1 centimeter. So I've defined the parameters that I need for my modeling, and start the pre-processing by \prep7 and select the element type. For the first element type, I want to pick 186, which is the higher order 3D structural element. I don't need to define a real constant, so I go directly to material properties, MP, EX for Young's modulus, material model 1, and the value was 49 E9 or 49 gigapascals. And now MP for material properties, PRXY, Poisson ratio in XY direction, material model 1, and the value was I think it was 0.3. And now let's define the density. So the value was 2800 and the label is dense. Now let's create some key points. So if I say K, leave the number blank, so ANSYS will pick the maximum available number, which in this case will be 1, and create it at the origin of the coordinate system, which is basically here. The next key point I want to create is in x of 0 but y of total height, which is created there. Then I want to move on to create a key point at big radius and total height. Now for the next key point, I want to come down by the length of the tab. So I go back there and say total height minus tab height. So it comes down. The next key point will be at the x of small radius, and the y will be this previous value minus the ramp height. So if I go back here and say RMP underscore HGH, and instead of big rad, I say small rad, that one is created. And the last key point I want to define is small rad by y0 to create a closed loop for me. So I say K small rad and 0. So the key points are made. Now I want to use them to create lines. So line between key points 1 and 2, lines between key point 2 and 3, 3 and 4, 4 and 5, 5 and 6, and 6 and 1. If I do Lplot, and then if I turn on the numbering for lines, do replot, I want to create a fillet between lines 3 and 4 and another fillet between lines 4 and 5. The command for that is lfilt. First is between 3 and 4, so NL1 and NL2 are the line numbers. Radius was FLT rad, defined here. So if I do that, and I forgot to put a comma there, so this fillet is created. Now I want to create another fillet between lines 5 and 4, so 4 and 5. So all the fillets are created. Now I can use all of these lines to create an area. So if I do AL, area with lines, and all the lines, and all the areas are created. So if I turn off the line numbering, do a plot. Now I want to rotate this area by the axis defined by the key points 1 and 2, which were here and there, to make a volume. The command is vrotate. I can give up to 6 areas, but I only have 1 area, so I give 1 and leave 6 blank inputs, so 2, 3, 4, 5, and 6. And now the key point 1 and key point 2 are the axis of rotation, and the angle is 90, and I want to give 1 segment. So if I take a look at it from, I didn't mean to do that, just wanted to bring this down a little bit. If I take a look at it in 3D, I have a volume. The next thing I want to do is to merge these areas to make one area for mapped meshing. So I do A cell S area. Or before doing that, let me see the area numbers. So if I do pnum area 1, do a plot, see that these areas are 3, 4, 5, 6, and 7 that I want to use to map them while with areas 1 and 9 when I mesh. So if I do a cell S areas, so select areas 3 to 7, and then do ACCAT or A concatenate all. Now an area is created, area 10. I can do all cell. Let's turn off the area numbering. Do replot. and actually do vplot. And now I want to activate the first element type, or element type reference 1, which is 186, material model 1, and I want to give it e size of 0.01 or 1 millimeter, 1 e minus 3, and I want to use vsweep to mesh this volume. So the volume is created and meshed as appropriately for me for this analysis. Now what I want to do is to apply the boundary conditions. Or actually, before applying boundary conditions, I want to mirror this by the xz plane, normal to which is the y-axis or y-axis. So I do vsim about y-axis. Oh, I should have said all. So vsim about y-axis, all of the area, all of the volumes, which is only one volume. And you can dismiss this warning because we had a concatenated area 10, which we can ignore. And if I do eplot here, and let me zoom all, this is a quarter of my geometry. But if I pick n cell at location y0, so selecting all the nodes at location y0, and do nplot, and turn on the numbering for nodes, and do replot, I see that some of the nodes, or most of the nodes, are falling on top of each other, which means this is not a solid part. So what I want to do is use nummerge to merge these nodes and say all, and I see that all of the nodes are merged. And before I all cell and do eplot, I want to turn off the numbering for nodes, pnum for node 0, replot. If I do nplot, okay. Now I say all cell and eplot. Now I want to fix the bottom surface of this specimen. So if I say n cell s location y minus total height, because it's in the negative y direction and it's the mirror of the top half, which the y for that was total height. So if I say minus total height would be this surface. And if I do nplot, just to see what I have, these are the nodes. And if I say d for degree of freedom, all the nodes, all degrees of freedom, 0, that is done. I can say all cell and eplot. Now let's take a look at the top surface. Now what I want to do is to select the nodes at z equals 0 and assign a z displacement of 0, and then do the same thing in the x direction. Select the nodes in the x of 0 and apply a x displacement of 0 to make sure that the quarter symmetry is applied to my model. So I say n cell s location z0 and plot, and then I want to say d all uz0, so all the nodes are restricted in the z direction. I want to do all cell, and then I want to say n cell s location. Now this time x is 0 and d all ux is 0, and all cell eplot. So see that the boundary conditions, the symmetry boundary conditions, are also applied. Now the model is ready for analysis. All I have to do is to apply the loads. So I say Finney here and start the solution. I want to create n type. I could give transient or time dependent analysis if I had nonlinear material properties, but here I am in the linear elastic region, so I can just use static analysis. And I want to print out everything, so outres, which means output the results, all the results at all steps and sub-steps. The first step was basically nothing. At time 0, which I want to use every small time, nothing is applied to the specimen, so I don't apply any loads, and I say number of sub-steps for this load step is only 1 because nothing interesting is happening. I'm going to say ls write, which means write this load step as the first load step, and the first load step is complete. For the next load step, I want to select the nodes at the top surface, which would be these nodes, and I want to move them in the y direction for 2 millimeters. And then I will say all cell eplot. The time at the end of this step is 30 seconds, so time comma 30, and the number of substeps I want to use is 30. And I want to make sure that this is a ramped loading, so I say kbc comma 0. 0 is for ramped, and if I gave 1 would be for step loading. And then I want to write this as the second load step. Now I can solve this. I can say ls solve. From 1 to 2, I had 2 load steps at every 1 increment. And it's going to be solving. So the first one is done, the first load step is done. Now I'm waiting for the second load step. It's going to take 10 sub steps to finish. So I can wait until the second solution is done, shows on the screen. And this progress mouse cursor will be gone. All right, the solution is complete. Now I can finish and start post-processing. So if I come here, if I take a look at this window, I can see all the load steps defined, and I can also do set. I had 2 load steps, and the second load step I want to have the last substep. I can just type last, and then take a look at the element solution for stress in y direction, which is that. Let me see if I could show it in that direction. So you can see that more stress is in the smaller radius section of the specimen. That's where necking would happen if we push this or pull this higher. Now if I do a PLE sol, EPL in the y direction, it shows that one as well. The elastic strain again is higher in the smaller radius section. Now let's define a path at the center line of this specimen. So I call this path and name it as v path with 2 points, a maximum of 30 data sets mapped to the path, and divide the entire length by 100 segments. P path for the first point, this is number 1 means first point, and I don't know the node number, but I know the coordinates, which is 0 minus total height and z0 in the Cartesian coordinate system. And then I have the second point at total height, so I want to change this number to 2 and see that. Next thing I want to do is to pdef for mapping on this path. VSY is the label I want to give, vertical S in Y direction. Item is S for stress and component is Y, and I want to average it. Now let's define the strain, VEY, EPL, elastic strain in Y direction, and average it. Now let's PR path, which means print path items, and I can define up to 6 labels. So let's say VS or VEY and then VSY. So a window like this will show up, and it has the length it has the elastic strain, and it has the elastic or stress in the y direction. And the total length of the bar is 16 centimeters. I can save this and import this into MATLAB or Python for more post-processing. Let's close this window and come to time history post-processing. And I want to particularly zoom in here. Now let's take a look at it in 3D and zoom further. I want to pick this center element. So let me do E cell SP. So select an element with picking. I want to pick this element and do E plot. So that is selected. For that element, I want to pick the stresses and strains. So what I want to do is to add data and come to element solution actually. In the stress, in the y direction, and pick that element. And then I have to pick a node. I pick that node and click apply. Now I want to do for plastic or elastic strain in the y direction. So if I click that, I have to pick the element again, this element. And the node I want to pick is that node. See the stress in y direction with respect to time, 30 seconds, and also the strain with respect to time. Now what I want to do here, something that I could do in this window, is to say this divided by, now I want to copy that part and paste it in here. Actually, because caps lock was on, it didn't actually do this. If I do it now, and if I change this ESL or S to EPL, and let's change this to EY3, the name. If I press enter here, it's going to ask me if I want to calculate, or it says it calculated. And if I print this or plot this, you can see that it's 49 gigapascals, which is the material property we defined. This is an isotropic. That's why it's not changing with respect to time. And also it's linear. So by dividing the elastic strain or stress by elastic strain, we got the Young's modulus of this specimen. Now if I do E-plot again, I hope I didn't do all cell, which I didn't. Next thing I want to do is add the elastic strain in the X direction for the same element and the same node. So this is negative. Now what I want to do in here is say EPL X and put a -1 times that and call this one 4 and EP, or let's call it PR. And let's see what it gives. It gives a value of 0.3, which is the Poisson ratio of my sample. But again, because this was a linear elastic material, isotropic as well, the values are the same as the material properties that I gave to my sample or analysis. So with this, we concluded a interesting example, a displacement control, time history analysis, and a Dogbone shape for a tensile loading